Welcome to our case study video, analysis of some alcohols, aldehyde, and ester in distilled separate with the alkaline AA60 gas chromatography. Our group members are Nur Alana Jahmid Kamar Zaman, Nur Atika Binti Muhammad Zamri, and Nurul Hanani binti Abdul Hadi. Our lecturer is Miss Anis Arifan binti Nur Azhar. Table of contents. We will start the video with the introduction and then proceed with the methodology and analysis and conclusion. We will also provide the reference we use in this case study. Introduction consists two parts, which are objective and general principle and concept of gas chromatography. For objective, to analyze some alcohols, aldehyde, and ester in distilled spirits with the alkaline A860 gas chromatography, and to study how the instrumentation of gas chromatography works using flame ionization detector. General principle and concept of gas chromatography. First of all, we need to know that gas chromatography is a technique for separating components based on their volatilities. Volatile components are the components that gets easily vaporized in a room temperature. The general principle of gas chromatography is a sample is being injected at the injector port and vaporized into the column. The sample is separated and then was detected by the detector. The four basic components of gas chromatography. Firstly is carrier gas. Carrier gas is chemically inert as gas as mobile phase. The mobile phase gas such as helium, hydrogen, and nitrogen are usually used as a carrier gas. The carrier gas flow through the instrument from a gas cylinder as shown as number 1 in figure. The carrier gas is kept in a cylinder gas which has a molecular sieve to remove water and impurities that may affect with the sample during the analysis. Second component is sample injection system. As shown as number 2 in the figure, the sample is injected using the syringe into an inlet of the column in a small volume and in the form of solution. A high temperature is applied to vaporize the sample solution to be a gas. The process should be quick as possible to provide a cause of band broadening and low resolution. The temperature of the sample port is usually about 50 Celsius higher than boiling point. There are two modes can be done, which are speed mode and speedless mode based on the concentration of the sample. Third component in the gas chromatography is column. Once the sample is volatilized, it passes down to the column where the separation between the molecules of the mobile phase and stationary phase occur. The less volatile molecules interact more with the stationary phase and move slowly while the more volatile molecule interact more with the mobile phase and move fast down the column. Once the separation done, the detection is done by the detector that attached at the end of the column as shown as number 5 in the figure. There are two types of column, which are pack column and capillary column. The column is placed in a chamber, or in the figure is in an oven to maintain a uniform temperature. Fourth components of the gas chromatography is detector. There are several types of detectors such as flame ionization detector (FID), thermal conductivity detector (TCD) and electron capture detector (ECD). When the sample is detected, the computer gives a peak with a respect to retention time of sample. The results is called chromatograph as shown in the figure.
Hello, my name is Nur Ananajiha binti Kamal Zaman, and now I will be presenting about methodology. For the sample preparation, firstly, mixed standard stock solutions will be prepared by adding defined amounts of each single standard compound with a microliter syringe. A stock solution of 10 compounds, each with a concentration of 1000 micrograms per ml, was prepared in a 60 ethanol to 40 water solution ratio. To achieve the required levels, 6 vials were made at each calibration level by striking varying amounts of stock solution in ethanol aqueous solution. The calibration standards were prepared at standard concentrations of 10, 30, 50, 100, 500 and 1000 micrograms per ml. An internal standard or IS was spiked to each calibration level, corresponding to an IS concentration of 440 micrograms per ml. The spirit sample were obtained locally from retail providers in China and introduced into the GC as need samples. Moving on, this table shows the operating conditions for the sample analysis using gas chromatography. Firstly, the GC system was 8860 GC with the FID detector. Next, the injection mode used was split or splitless with a split ratio of 30 to 1. Thirdly, the type of column used was capillary column. Fourth, the carrier gas used was helium. Next, to obtain well-separated peaks, the column or oven temperature was set using temperature programming, where the temperature is raised from 40 degrees Celsius continuously at ramp 5 degrees Celsius per minute to 100 degrees Celsius. Then, from 100 degrees Celsius, the temperature was raised continuously at ramp 10 degrees Celsius per minute to 200 degrees Celsius. 6. The injection volume was 0.5 microliters. And lastly, the detector used was FID.
Hi, my name is Nurul Hanani binti Abdul Hadi and I will be explaining the analysis part. Figure 1 shows a typical chromatogram acquired by the system with 10 standard compound and 1 addition standard at concentration of 100 microgram per ml. To improve the precision of quantitative analysis, the approach of internal standard is applied. An internal standard is a chemical with known concentration that is present in every examined sample. Internal standard can be used with either calibration curve or the standard addition procedure. From here, we can calculate the concentration of the unknown. The internal standard objective is to act similarly to the analyte while producing a signal that can be distinguished from the analyte. In other words, any factor that influences the analyte signal will also affect the internal standard signal in the same way. As a result, the analyte signal will be less variability than the ratio of the two signals. The identification of this compound is done by comparing the GC or gas chromatography retention time of standard chromatogram and the sample chromatogram. The retention time or RT is the amount of time it takes for a compound to move from the ejection port to the detector in our gas chromatography, and it is measured in minutes. For instance, in figure 1, the chromatogram of standard solution ethyl acetate has approximately 4.5 minute retention time. By comparing this with figure 2, the chromatogram of the sample, at the same retention time, the peak of ethyl acetate appears. The sample produced the peak at the same retention time as a standard under identical condition. So it is identified as the same compound due to the same retention time. Same goes to isobutanol. By comparing retention time of the standard chromatogram and the sample chromatogram, we can identify the 12 peak in the sample chromatogram as isobutanol because both compound has the same retention time, which is 10 minutes. Next, there are several factors that can influence the separation in gas chromatography, which are volatility of the compound, polarity of the compound, column temperature, flow rate of the gas through the column, and the length of the column. However, in our result, the factor that affect the peaks order is volatility and polarity. Referring to figure 2, if we compare ethyl acetate and ethyl lactate, ethyl acetate elute first, causing the compound peak to appear first with shorter retention time, and ethyl lactate peak appear later with longer retention time. This is because ethyl acetate has 88.11 gram per mole molecular weight and 77.1 Celsius of boiling point, while ethyl lactate has higher molecular weight, which is 118 0.13 gram per mole and 154 Celsius of boiling point. But what does this information mean? Well, theoretically, the higher the molecular weight of a compound, the higher the boiling point, resulting low volatility. Separation factors stated that the low boiling point components or high volatility components will travel faster through the column than the high boiling point components or the low volatility components. Since ethyl acetate has lower boiling point, it elutes before the ethyl lactate. Next, we will take a look at ethyl acetate and methanol. Methanol has lower molecular weight and boiling point than ethyl acetate, which is 32.04 gram per mole and 64.7 Celsius of boiling point. But why does ethyl acetate elute before methanol? This is because the polarity of the compound stated in separation principle that the polar compound will move more slowly, especially if the column is polar. In other words, the higher the polarity of the compound, the longer the retention time. Ethyl acetate is an ester and methanol is an alcohol. If we refer to the polarity of organic function group in increasing order, ester has lower polarity than alcohol. So that is why ethyl acetate elute before methanol, as we can see in the result. Since we use a flame ionization detector or FID, we will discuss the limitation and the advantages. FID has a benefit of responding to all hydrocarbon gases, including methane, and having a large measuring range. As we can see in the slide, FID can measure the organic substance concentration at a very low, which is 10 power of negative 13 G per S to 10 power of 7 G per S. And it has a rod construction. Having a rod construction of FID means it is sturdy, simple, reliable, versatile, and easy to use. Moving on to the limitation. The limitation of FID is it is sensitive to carbonyl, amine, and alcohol group. The FID destructive nature means that it cannot be directly connected to other GC detector, which is one of its drawbacks. However, if a portion of carrier gas stream is split between FID and other detector, a FID can be still utilized in combination with other detector.
In conclusion, the experiment was a success as the alcohols, aldehydes, and ester in distilled spirits was analyzed using the Agilent 8860 gas chromatography. Furthermore, we also studied how the instrumentation of gas chromatography works using FID.